Okay, it's a pleasure to have Chris here for the second half of the talk on K-theoretic Tutte polynomials of morphisms of matroids.
Okay, once again, thanks for having me. This is a joint work I did with Radhika and Tim. And let me start by saying what kind of some sort of our goals were and what motivated this work. So in recent times, there's been a lot of developments concerning combinatorial object called matroids, which essentially one can think of as hyperplane arrangements or combinatorial data kind of storing some information about points in the Grassmannian. So one can think of matroids as coming from points on Grassmannians. In particular, to me, what was very interesting was this development of Hodge theory of matroids. And at the back of my mind, in most of my PhD years, I was kind of dreaming that there will be some sort of Hodge theory of matroids or some similar kind of development in what are called Coxeter matroids. So Coxeter matroids has been studied relatively well before, but not in this new light in terms of tropical geometry and law concavity and whatnot. So one can think of it as if matroids are kind of points on Grassmannians, then Coxeter matroids are basically take any reductive Lie group, mod up by a parabolic subgroup, look at some combinatorial data of a point on there. Now that's way in the future now. I realize, yeah, perhaps we're not quite ready to tackle that. So the next kind of generalization to matroids is what one can call matroid morphisms. Some people also call this flag matroids, or really two-step flag matroids. So we're taking a baby step here, and turns out even that is somewhat involved, where we replace Grassmannians by partial flag varieties. And we're going to try to study the combinatorics of these things geometrically in the same way that we have studied matroids by looking at Grassmannians. So let me go back to the matroid story again. So what happened in the matroid? So the point of departure in our case is work by Fink and Spire. And what they did was as follows. So let's consider the following diagram. So I have Grassmannian of r-dimensional planes in n-dimensional space. I have partial flag variety of 1, r, n minus 1 in n-dimensional space. So this is a line inside r-dimensional space inside a hyperplane. So that's the point of this. I have kind of the obvious kind of forgetful map where I just forget the line in the hyperplane and just keep the data of the r-dimensional plane, and that's the map to Grassmannian. And then I have the map to similar map to Grassmannian n-1n, or I forget everything but the hyperplane. Also the other Grassmannian 1, n, or I forget everything but the line. These are actually just projective spaces. So I have a map to product of two projective spaces. So this is pi of, let me name that n-1, 1. And this projection with pi of r. So these are the maps. And throughout this whole picture, there is a torus acting on the background. So there's this algebraic group, C star to the n. Let me name that torus to be T. And it acts on the Grassmannian just by its action on the n-dimensional space in the standard way. So what did Fink and Spire do? Well, if someone hands you a point on the Grassmannian, which is basically the same as an R by N matrix, a full rank R by N matrix, you get a matroid. Let me denote that by M of V by looking at its columns. So the independent subsets of this matroid are exactly just independent, linearly independent subsets of these columns. So you have this matroid. And the question was, how can I express the top polynomial of this matroid in some geometric way? Can I see the top polynomial geometrically? We had many different combinatorial descriptions for it. And turns out there's a really beautiful answer. And what one does is first you consider the torus orbit of that point on the Grassmannian, take its closure, look at its structure sheaf. So this is a subvariety of the Grassmannian. We can look at its structure sheaf and tensor that by the ample line bundle on the Grassmannian. And then to this thing, what I'm going to do is pull it back and then push forward. So all the pullbacks and push forward in this case are, well, pullback is just pullback, and push forward, I really mean the derived push forward. So for those who are actually thinking about this K-theoretically. And what they showed is that this now resides in the K-ring of Pm-1 cross Pm-1. This is known to be isomorphic to ring with two variables mod the variable to the power of n. So I can consider what this class is expressed in terms of these alphas and betas. And the theorem was that if I plug in, let's see, alpha comma beta here, that exactly equals this class. That I wrote down above. So basically the lesson here is that this diagram of pulling back and then pushing forward to here gave me the top polynomial. So that was their story, and it's quite beautiful. And immediately we can start asking, okay, what if I just replace the Grassmannian on the left side? So that was the starting point of our project. So before telling you exactly what we did, let me set some definitions. If I have two matroids, M1, M2, on a common ground set, and let's say they have total rank R1 and R2. And R2 is greater than or equal to R1. The definition of matroid morphism, also called matroid quotient, denoted in this way, is that the following inequality is always satisfied. So this is a combinatorial condition, which is not too important for today, but I should write down some definition. So matroid M1 is called a matroid quotient of M2, or equivalently one says there's a matroid morphism from M2 to M1 if this inequality is satisfied for all B contained in A contained in the ground set, the common ground set of these two matroids. And geometrically, these exactly correspond to flags of two vector spaces. What do I mean by that? Recall that if I have a linear subspace in Cn, given by a row span of some R by n matrix, That's just a linear subspace that gives me a matroid. Let's call it M of V1. And I have another linear subspace V2, and V1 is contained in V2. Then I have another matroid coming from that data. And the statement is that these guys always form a quotient. So geometrically, matrix quotients are literally just inclusions of linear subspaces. It's not much more than that. So that fits with our picture very well. We just wanted to replace the Grassmannian by partial flag variety. So let's do that. And that's where, in some sense, trouble starts to begin. So here's one diagram. Let me label it 1. So I have R1, R2, and so this is now a space of flag of linear subspaces dimension R1 and R2. And I can consider this kind of diagram. So basically exactly the same as before, but Grassmannian replaced with the flag, partial flag variety. I think I saw a question in the chat. For graphs, what is this quotient notion? Let's see. It's a little bit tricky because quotient of a graphic matroid may not be graphic. So it's a little bit harder to see. But if you have a graph homomorphism where the edges are going to edges and vertices go to vertices, the two graphic matrices do form a matrix quotient. So if someone handed you a graphic matrix and then said, here's a matrix quotient of that the one that is quotient need not be graphic at all. But if I had a graph homomorphism, the two matrices form a matrix quotient. Okay, so that's going back to this. This is the first diagram, and this is like the natural thing to do, right? Like this is like the first thing one would try. Now let me also mention this another diagram where the lower level looks exactly the same. But at this top part, let me put this tilde here to differentiate it from the other one. And this one, the points of this kind of funny tilde flag partial variety of 1, R1, R2, and -1 is as follows. You consider lines contained in the bigger vector space and hyperplane containing the smaller vector space, and the smaller vector space is contained in the bigger one. So if you're if you're used to like partial flag varieties, this might make you a little uncomfortable. And for sure, I was not too thrilled to realize that one might need to actually look at this picture. But let me try to tell you why this picture is also important. So let's begin with this kind of really funny looking geometry first. So any other questions at this point? Okay. So why do we have to look at that really kind of funny looking geometry? And it actually goes back to a paper, in fact, a series of papers by Las-Vergnes, 75 and onwards. So Las-Vergnes has, I think, literally 6 papers, series of 6 papers titled Top Polynomials of Morphisms of Matroids, which was like, when we started our project, we were like, oh, that has to be the answer. And it's literally titled Top Polynomials of Morphisms of Matroids 1, 2, 3, 4, 5, 6. So he had like a series of 6 papers. And there, the definition of a top polynomial of a matroid morphism was as follows. So I have two matroids once again, forming a quotient with ranks R1, R2. Then he defined the following version of the top polynomial. Let me denote that by LVT for last Wegener's top polynomial, and it's a polynomial in three variables, x, y, z. And it looks quite similar to the definition of the top polynomial where you sum over all subsets of the ground set. So I'm summing over once again all subsets of the ground set of these matroids. I look at R1 minus rank of the subset in the first matroid. This one, I look at the difference between its cardinality and the rank of the second matroid times z to the power of, let's see, what's the best way to write this? I think this is probably good enough. Minus R1 plus. So it's kind of funny looking definition. It's a polynomial in three variables. And he proved quite a few things about it. They're all combinatorially interesting. And if you plug in, for example, 2, 2, 1, you get the number of subsets back. It satisfies deletion contraction. Has fairly nice properties. So when we looked at this, we're like, okay, let's hope that this comes from this kind of pullback push computation. And no matter what we kind of try to do with this geometry, there's not much that seemed to work. But turns out really to get the last Wegener's polynomial, looking at this kind of really funny looking geometry just does the job. So let me tell you what our theorem is. So in this diagram, I haven't really labeled these. So let me label this pi, but with tilde, just to differentiate from the other one. So I have, once again, these two maps. I do the exact same thing, or almost the exact same thing. Say I have matroids M1 that's equal to a matroid associated to a linear subspace V1 that forms a matrix quotient with M2 that's associated to a linear space of called V2. In other words, I have inclusion of two vector spaces. ICN. Let me denote this by V dot. So I have a point in the flag variety. Once again, I look at its torus orbit, take its closure, look at its structure sheaf, and then here I tensor by the ample class coming from, I guess it's not ample, the class coming from the ample class of the Grassmannian R2n. So I pull back the O1 from that to the flag. So I get this class. And then on top of this, I need to tensor this by wedge powers of what I'm going to define soon as some quotient of two vector bundles. Take this whole thing and then pull back push. So this kind of somewhat ugly looking thing. And then I keep track of what wedge power of this quotient bundle that I did by m. And the theorem is that this equals to LVT of m1, m2, where you plug in alpha, beta, and z. So almost exactly the same thing as Think and Spire, but for Las-Fergness top polynomial. And it was kind of funny that we had to look at this, like funky looking, not really a flag variety, kind of variety at the top. But it seems like, that's just how the nature handed things to us. Now, I haven't really kind of told you what this thing is yet. It's not too important, but these guys come from the two tautological bundles. So on the Grassmannian, say Grassmannian R1, n, there's a tautological bundle as such, where the tautological subbundle S1 is one where if I'm looking at a point, let's say V on the Grassmannian, the fiber over that is that vector space V. So that's the tautological bundle. Same thing for S2, and I look at the quotient of those two. In other words, this is a vector bundle on the partial flag variety, where over the point V dot, the fiber is V2 quotient by V1. So that's the vector bundle over that. So in this case, we got somewhat of a satisfactory answer in terms of what is this Las-Fergness polynomial K-theoretically, and we're like, here it is. And one can say a little bit more about Las-Fergness top polynomial now that we know about the fact that it arises K-theoretically. And we can, in fact, recover many of the combinatorial things that Las-Fergness has established, but not too much new. It's just satisfying that there is a geometric way to look at this combinatorial quantity that has been defined before. Now let's go back to the more geometrically natural picture. So not this funky like line inside the bigger one and hyperplane containing the smaller vector space. The actual flag variety. So let's take it as a definition.
Chris, can I ask you a question? So,
Sure.
So I guess these dot polynomials have this deletion contraction. So are these relations quite non-trivial on the other side, on the geometry? Like,
Yeah, to see the deletion contraction geometrically is rather tricky. But really, when one tries to compute this, maybe I'll have time to get to it today, but really one computes this by doing all this torus equivariant push-pull computation. And in that context, deletion contraction is a little more apparent. Like once one kind of gets down and dirty and tries to actually compute these, it's not too hard to see. But just from what I've written down, deletion contraction is highly non-obvious. Okay, so going back to the more natural geometric picture, let's take it as a definition. If I have matrix quotient m1 by m2 given by an inclusion of vector subspaces, how should I define a polynomial in xy? Well, I define it such that whatever I kind of claimed before is true. So if I plug in alpha beta, K classes in the product of two projective spaces, that will exactly be the pullback push forward. If once again I look at the torus orbit closure, this time I actually tensor it by the ample class in the flag variety. Well, there's not the ample class, but pull back the two ample classes from Grassmannian and sum them up, and then do a pullback push forward. And unfortunately, this polynomial is really not like, it seems quite hard to analyze combinatorially. And I'm ashamed to admit that like we have not been able to say so much. So let me just tell you kind of the most salient features after some of the more immediate ones. So there are some facts that are like fairly easy to verify, and that's been listed in our paper. So let me skip over those. But kind of the two most, I think, non-obvious ones in our paper are as follows. The first thing is that if I plug in to x and y, 2, 2, it is not equal to 2 to the n, or 2 to the size of the ground set. Instead, it equals the following number of subsets in E such that A is independent in the bigger matroid, and it is spanning. In other words, it has full rank. In other words, it contains some bases in the smaller matroid. So if we ignore this factor, now if we plug in 2, 2, it actually counts what are known as, well, some people call this pseudo bases. In my paper with June, we actually just call this the bases of the matroid morphism from M2 to M1. So these were considered before, and if you consider M1 here being actually just the empty matroid, where you have the empty set being the only independent subset, this actually counts the independent subsets. If M1 equals to M2, this is the basis. So so this is how it generalizes the notion of basis for morphisms. So this counts the number of bases somehow when we plug in 2, 2 now. That was the first thing. Another thing that we noticed is that, so if you try to do some sort of deletion contraction, it's, yeah, like rather, yeah, it fails dramatically. So instead, we can look at the following. Take a common, just regular one matroid and consider contracting and deleting by the same element. That always forms a matroid quotient. That's a fact. And this satisfies a deletion contraction-like looking thing. So if I stopped something at like this, it would be all great, but that's not so. Turns out this kind of a little more weird looking deletion contraction holds. Now, other than this, there are so many other kind of combinatorial things that we would like to know about this K of T that we have no idea about. And in some sense, we started to think maybe this is just not the right thing to do. Maybe this kind of the more geometrically natural looking thing doesn't seem to actually have good combinatorial properties. So this is, in some sense, one can think, this is maybe more of a negative result than an actual result. So that was unfortunate, but we thought that these two results are at least quite interesting to look at. Now, we have listed some kind of future directions for both Tutte polynomials, the one coming from Las-Vergnès and one coming from this more geometric case. And it seems like they both have merits in the sense that Las-Vergnès has good combinatorial properties, and we can formulate some new law-concave conjectures built on that. For this new geometric one, we have evidence that it should generalize what Spire defined as his G polynomial. So Spire's G polynomial was this somewhat mysterious-looking polynomial that controls the number of subdivision or parts in a subdivision of a matrix polytope. And it seems like this, in the geometric case, in the flat case, the more geometrically natural-looking polynomial as defined here has better relation in terms of generalizing that picture. So if I may, let me just take 1 or 2 more minutes to show you, if you're interested, you can kind of jump in and start experimenting with a lot of these things. Let me stop my screen share here. And screen share on my laptop. So are people seeing some sort of GKM manifolds thing on the screen? Yeah.
Yep.
So this is a Macaulay 2 software that I wrote with Rifik. And much of this was developed while we were writing the paper with Radhika and Tim. And for example, if you would like to see the computation for the K-theoretic Tutte polynomial, the geometric side, yeah, so you can kind of actually do the computation yourself and see how they come out. And it seems like many of the computations that we did can be done for arbitrary Coxeter matrix, but none of them has been implemented at this point. And in fact, there are many, many more things that we would like to implement in this package that has aided in doing many of the computation with this project. And yeah, so you can really take this as an invitation if you are interested in this kind of topic, or open arms to whoever would like to contribute. And of course, if you contribute enough, we'll also list you as an author when we actually try to make this as a published package. So if you're interested, please let me know. And with that, let me just finish here.